So it occurs to me that learning how to draw funny little bow tie looking things and calling them chairs may not be the most interesting thing in the world to you. And it's always good to justify why we're learning about something with a reasonably real world connection. So I want to give you an example from life and nutrition that explains why we care about chair conformations. And the real reason is that in biology, shape is everything. Shape of a molecule will determine whether it can bind to a particular receptor and trigger a particular response, or whether it fits in an enzyme active site and can be modified or broken down by a particular enzyme. And a great example of this comes from carbohydrates. So you don't need to draw this down. I'm just going to draw a couple of subunits of a long biologically relevant carbohydrate. Carbohydrates are made up of 6-membered ring subunits where one of the atoms in the ring is an oxygen, but they still adopt similar sorts of shapes as cyclohexane rings do. And then one of the reasons they're called carbohydrates is because there's one atom of oxygen and 2 atoms of hydrogen for every atom of carbon you've got in these molecules. Each of the subunits here is actually glucose. And the way that these glucose subunits are connected together, and maybe it would be useful to number the atoms, carbon atoms of the ring. They're connected via an oxygen, and that oxygen is equatorial to carbon 1 and equatorial to carbon 4. All right? There is another carbohydrate made of exactly the same subunits, only the shape is different. So in this case, the oxygen is going to be axial at carbon 1, but still equatorial at carbon 4. And again, don't worry about drawing this. If you want to see the structure again, you just need to Google the molecules. I'll give you their names. All right, I think I've got everything in the right place. So over on the right, the oxygen's axial with respect to carbon 1, but equatorial with respect to carbon 2. Both of these are made of glucose. The one on the left is cellulose, fiber, plant cell walls, components of fruits and vegetables, and over here you've got starch. Okay, what do you know about starch versus cellulose in terms of nutrition? You can digest starch, break it down to carbohydrates, or rather break it down to glucose. Last time I told the class to go suck on a saltine a cracker and watch it sort of turn a little bit sweet in your mouth as you suck on that soggy cracker. We decided that was maybe an effective insult to try out with roommates. So go suck on a saltine cracker. Yes, but you can't hydrolyze cellulose, and it's because of the linkage. That connection doesn't fit in the enzyme active site like that connection does, and so you don't have enzymes to break this down. Some bacteria do, and so this is how cows are still able to eat grass but gain nutrition from it, because they have their gut flora are able, or microbiome is able to break apart those linkages. So shape critical and matters a lot. And this is an example of how such a subtle difference as axial versus equatorial can make a large difference in what molecules can do. All right. Any questions? Yeah, go ahead.
I'm wondering, does that equatorial versus axial and equatorial determine how long the chain can actually be?
Does the axial versus equatorial limit chain length? I don't think it limits chain length, though it does influence chain shape. Cellulose tends to be long and extended. Starch tends to adopt a long spiral shape. Yeah, it's interesting. Just as an aside, if you've ever heard of the sugar lactose, it's a linked, you've got a glucose molecule linked to a galactose molecule. And actually, the only difference between glucose and galactose is that the hydroxy on carbon 4 for galactose is up instead of down. And if infants of mammalian infants express an enzyme in their guts that breaks apart that equatorial linkage. But for most humans over the course of human history, there was no longer a need to survive on milk, and so the expression of that enzyme got turned down in juveniles and adults. However, at some point in human history, there was a mutation or a series of mutations that occurred in an area of the world where people were starting to domesticate animals and starting to try to use milk and cheese and other things, and it became an advantage to a selective advantage for some of those humans to start to express more of the enzyme that hydrolyzes that linkage. The enzyme is called beta-galactosidase, and it refers to this equatorial linkage. And if your ancestry is from that part of the world where that innovation first occurred, you probably are not lactose intolerant. But if you're from anywhere else in the world, you maybe are. And it all has to do, again, with this particular shape. So, all right. I don't know what else we need to say about that. I'd like to make sure you guys have the tools to draw chairs properly and to convert between one chair and another, and to tell which chair is the most stable. So I think we'll begin with a review of the chair flipping rules. And before we do that, actually, I want to start with how do you take an overhead view of a molecule and convert it into a chair conformation view. And I'm going to start with two different versions of 1,2-dimethyl cyclohexane. You've got the cis version and you've got the trans version. Notice that they are different, right? In the cis version, the methyl groups are on the same side of the ring. In the trans, they're on opposite sides of the ring. Though the methyl groups are still, I mean, if we numbered the carbons of the ring, the methyl groups would still be bonded to carbons 1 and 2. So the connectivity is the same, but the structure and shape is not. We will call these stereoisomers. Actually, in the same way as we would call cellulose and starch stereoisomers. And that's a word that we're going to introduce more in Chapter 5, but you just as well get it in your mind now. Stereoisomers are molecules that have the exact same connectivity but different shape, so that they're not the same thing. So how do we draw a reasonable chair conformation for either of these? Well, start out with drawing the chair, and then arbitrarily choose to put carbon 1 at either an up carbon or a down carbon. Doesn't matter which, because we're eventually going to draw both chairs anyway. You got to pick somewhere to start, so just pick one and make sure you draw the chair consistently. So for us today, I'm going to say let's put carbon 1 at this up position in the upper right corner, and let's put carbon 2 at the down position in the lower right corner. Notice, and this will be important later in chapter 5, if I number the rings, if I'm looking down from above and I number the rings clockwise here, I need to do so here as well. So at carbon 1, the methyl group is supposed to be up. So in my chair drawing, which of the two positions at carbon 1 is up? Is it the axial or the equatorial? Axial. You can tell that because up carbons have up axial substituents. A substituent is the group that's attached to the ring. I'm going to fill in the hydrogen here that was implied but not originally shown. On carbon 2, the methyl group is also up over here. So when I draw it in the chair, I must also draw it up. Now the up position at carbon 2 is going to be equatorial. All right. Well, what if I had instead chosen to start by putting 1 at a down carbon? We can do that, only we have to move carbon 2 here, except not calling it carbon 3, goodness. Now carbon 1 is at a down carbon. Carbon 2 is at an up position in the ring. So for carbon 1, the up methyl group now has to be equatorial. And for carbon 2, the up methyl group now has to be axial. All right. So those are actually the two different chair conformations for this molecule. We'll call it one chair and the other chair. Or maybe if there are any musicians among you, we'll call this first chair. Especially any trumpet players among you, there's first chair and then there's all the other chairs because trumpet players are competitive. At least that's what they tell me. I was one 20 years ago. And it's very sad to remember the glory days and how I can't really play anymore. But that's that. So suddenly I'm all thinking, well, Josh, if you really wanted to, you would have done it. So why are you complaining about it? And then I'm thinking, this is neither the time or place to have an existential dilemma about trumpet playing and so on. So sorry about that aside. You've got the one chair and the other chair. They are actually in equilibrium with each other. The way we get from one chair to the other chair is, let's highlight the up carbons in purple, and let's highlight the down carbons in orange. To get from one chair to the other, we're going to push the up carbon 1 downward, and at the same time, carbons 2 and 6 will have to adjust upward. Maybe I'll number the rest of the atoms in the ring. And then with the group, with atom number 4, that's a down carbon, we're going to push that upward. And then the other two, 3 and 5, will have to adjust downward accordingly. So what used to be up on the left is now down on the right, and so on. And the fact that we are taking this up position carbon 1 and rotating it downward brings that up methyl group, axial methyl group, into this equatorial position. Yeah?
I was wondering, when you're counting the carbons, you said they have to, when you count the carbons in the original line structure,
Yeah.
you have to make sure that it stays counterclockwise or clockwise. Why is that? What did you get it counterclockwise?
Yeah, the question is, why am I telling you you have to number consistently? It has to do with something that won't make a lot of sense until we get deep into chapter 5. We are viewing this ring from above, as though we're floating over the page and looking down on it. if you were to draw where on the chair, sort of where our eyes are at, the eye would be hovering over the ring. If you numbered it counterclockwise instead of clockwise, if you did it clockwise here and counterclockwise there, you're going to get the mirror image of the compound you're talking about instead of the one that you're talking about. That doesn't make any sense now, but it will in just a little bit. All right. So, other questions? Folks at home, I forgot to ask, is the audio coming through? I assume it is because you're all not saying anything. Okay. So notice what happens when we go from one chair to the other chair. Up carbons become down carbons, and down carbons become up carbons. Notice that axial groups go equatorial and equatorial groups go axial. So this is the last shall be first and the first shall be last kind of action. But what doesn't change is up substituents stay up and down substituents stay down. Methyl group attached to carbon 1 is up in our drawing to the left. In the other chair, it is still up, only it's up equatorial. The down position is occupied by the hydrogen. So chair flipping does not interchange cis and trans. And in fact, if I were to draw one of these trans, the chair conformation for one of these, or for the trans stereoisomer, there is no way to interconvert this chair of the cis isomer with this chair of the trans isomer by rotation of bonds. You can't do it. It would require you breaking bonds to do, okay? That's really critically important. Up stays up and down stays down. I warn you because I will provide lots of opportunities for you to make that mistake on the upcoming exam. So let's just fix it now instead of after the fact, and then you get the points and you're happy. And I don't have to explain it after the fact, and I'm happy, right? Just take care of it that way. Actually, I'm always happy to explain after the fact. I'm sorry. A couple of questions that came up the first time that I think some folks might have. As you look at the first chair versus the other chair, it looks like all I've done is moved the numbers. And that's actually not the case. The reason I've redrawn the other chair in this way is because it's very difficult to draw a chair with an up carbon in the upper left-hand corner. You would sort of have to do this and then remind yourself that this side was in front and this side down here was in the back. And that gets a little bit optical illusion-y and kind of confusing. So instead, what we do is we flip the chair and then we rotate it such that carbon 1, which used to be up, is now down, and that down position we're drawing in the lower right-hand corner where it's easiest to do. Your text will sometimes give you this idea of chair flipping by drawing something like this. And that is mostly marketing. It's mostly just to give you the idea that the chair flipping happened. Though if I continue to number 1 and 2, actually all that's happened is I was viewing it from this side or this side, and now I'm viewing it from this side. I've just rotated it a little bit. So the real way you can tell if a chair has flipped is up carbons go down, down carbons go up, axial goes equatorial, equatorial goes axial, but up substituents stay up, down substituents stay down, worlds without end. Okay? So other people have asked, well, what if I draw, how did I know where to put 1 and 2? What if I draw the wrong chair? Well, it turns out that as long as I put 1 and 2 at, as long as I put 1 at an up carbon and I put 2 in the right clockwise direction, it doesn't matter where I put the substituents, I've drawn the same molecule. Can you see that the molecule here on the bottom is just like you hold both sides of that ring and do steering wheel action to turn it about a third of the way around? Second, what if I chose to put carbon 1 at a down position instead of an up position, and I say, great, good for you, you've just drawn the other chair. All right. Okay, so your goal when doing this will be first to faithfully reproduce in chair format the correct molecule, that is, with the correct groups being up. All right? And then after that, you will need to choose which is the most stable chair. All right. Questions so far? Anything? Okay. So when could you show us this in the program? Which program? Oh, sure. Here is the program Spartan. This is not the wiggly one. Here is a methyl group at an up carbon. Colton wants to clarify that the other chair that I just drew, yes, this is the other chair for the trans stereoisomer because one methyl group is up and the other is down. So these two are in equilibrium with each other. Okay, so this is cyclohexane that's just bonded to one methyl group. It's in the axial conformation. It's at an axial position, though you can sort of see that it's not perfectly axial. See how that bond between these two atoms is sort of tilted relative to these carbon-hydrogen bonds. We'll talk about that in a minute. Here is the equatorial conformation where that methyl group is equatorial. All right, folks at home, are you seeing this Spartan program well enough? I know that the movie one was kind of trouble, but is it coming through okay? All right. If it's all right, we're going to continue using this Spartan program to talk about the difference between axial and equatorial. All right. We'll start with the axial substituent. There are two problems with having a group axial versus equatorial. The axial position is crowded in two different ways. First, you have these other axial groups that are 2 bonds away. So if this is carbon 1, this is 2, this is 3, these two substituents, the methyl group and the hydrogen, are at positions 1 and 3. We call this a 1,3 diaxial interaction. And we can draw that here. Let's actually redraw the chair for, actually I'll just draw a chair with a single methyl group on it. Carbon 1, 2, and 3. This is the interaction between the steric repulsion between the methyl group or whatever group is there and the other group that's axial on the same side of the molecule. We're going to call a 1,3 diaxial interaction. And it's just that those two groups are in the same area and they're bumping into each other. It's just electron-electron or Coulombic repulsion. And actually, you can see in this image the reason that that methyl group tilts away from a perfect chair is actually to relieve the 1,3 diaxial interaction. It might actually be useful to show this in space-filling spheres to get a sense for how close that methyl group is to those other axial hydrogens. Yeah?
Is it also 1,5 also?
1,3 and 1,5, though, yes, that's correct. Though organic chemists will say they're both sort of 2 bonds away from the one substituent. So 1,3, 1,3 prime, I don't know. Either way is fine. Okay, so that's just regular steric repulsion. It comes from Coulomb's law because like charges repel. The second issue, so notice that is not a problem. I like that one better. That's not a problem in the equatorial conformation, because now look at the relationship in space between the methyl group, the up methyl group, and the up proton on 2 bonds away. See? The next issue has to do with torsional strain. And Colton, your question here from the chat is really good. I'm gonna address that in just a second, if that's okay. Now let's look at another problem with the axial conformation. And to do this, we're going to look down the bond between the methyl group and the adjacent, between the carbon that bears the methyl group, carbon 1, and then carbon 2. Carbon 2's in the back, carbon 1's in the front. Notice that is a staggered conformation. But notice that what is the relationship between the methyl group on carbon 1 and this ring carbon in the back? There were 2 words we used for staggered conformations. One was gauche and the other was anti. They're gauche to each other, right? And we said that having 2 groups gauche is not as good as having 2 groups anti to each other. So one of the problems with having the axial, a substituent in an axial position is it's gauche to the ring on the adjacent carbon. And that's true on both sides. No matter which bond you look down, methyl group is gauche to this carbon, and it's also gauche to that carbon, right? So to illustrate that, maybe we'll take a slightly different view, and let's just look from the front down carbon 2, the bond between 2 and 1. We'll put 2 in the front. Here is carbon 3 of the ring. In the back, your axial methyl group is pointing upward, your equatorial hydrogen is pointing downward, and then you have, we'll say atom 3, and then I guess 4, 5, 6. And 3 and 6 are, of course, connected by 4 and 5. We're not looking at that. In the axial conformation, that methyl group is gauche to the ring. All right? In contrast, if we look at the equatorial conformation, where that methyl group is at an equatorial position, and then we look down the same bond between carbon 2 and carbon 1, this time sort of from the side, what we would see, here's carbon 2 with an axial up proton and an equatorial down proton, and then there's carbon 3. In the back would be carbon 1 with a methyl group up equatorial, proton down axial, atom 6 equatorial. And then notice how in the equatorial conformation, the methyl group can be anti to the ring. So, why is equatorial better? Going from having a large substituent axial to equatorial is favorable because you relieve the 1,3 diaxial steric repulsion. And second, you relieve torsional strain, by which we mean having the substituent gauche versus anti to the ring. Yes?
On the first configuration, you refer to carbon 6 and 3 being connected.
Yeah.
Do you mean that they're gauche? Is there something more significant?
No, there's just atoms 4 and 5. They're all part of the same ring.
Oh,
I'm just not drawing the rest of the ring because I
cool.
didn't want to. Yeah.
You had a substituent on carbon 1 that was an alcohol group, and then you had carbon 2, I believe, if you have like an oxygen instead of a carbon.
Uh-huh.
You can do hydrogen bonding between the two. Would the gauche be more favorable?
Okay, yeah, so there's a couple of interesting things to do with that question. Folks at home, someone in class asked about, I think, what if these two methyl groups were instead something, what if they were in a, I'm not sure I can think of a situation that would describe what you're asking. I think the question was whether or not having an oxygen in the ring might allow for the opportunity of something like that, hydrogen bonding. It's a good idea. There are a couple of reasons. The hydrogen bonding actual angle, hydrogen bonds are best when at a close to 180 degree angle, so the angle there's not optimal. And there's another reason why that isn't necessarily the best arrangement, but I'm going to punt on that because it's more of a 352 topic. Someone did ask, as we look at the trans conformation and think about having methyl groups or rather axial versus equatorial, someone, Colton, I think you noted at home that if we look down this bond between 1 and 2, the methyl groups would actually be gauche to each other. We'd see on carbon 2, methyl group equatorial, and then on carbon 1, the methyl group equatorial. Yes, you are right. Those two methyl groups are gauche to each other, but they would both be anti to the ring on either side, and so it's probably a trade-off. So yeah, you might predict actually that the trans equatorial conformation is not maybe as stable as you would expect because of some of this gauche repulsion between methyl groups, but it's still going to be more stable than the axial conformation. All right, so let's figure out how to sort of quantify this. It turns out that you can measure the equilibrium constant between the chair and the other chair. And for the methyl group, that equilibrium constant is consistent with a free energy change going from axial to equatorial of negative 1.74 kilocalories per mole. And based on the relationship delta G equals minus RT ln K, you can calculate that at equilibrium, there would be a little more than 10 times more equatorial than axial conformation. This free energy difference you can measure experimentally, and this is the origin of the so-called A value. A is for axial. So the A value tells you how much worse it is to have some substituent axial versus equatorial. So free energy differences are favorable when negative. So the value of going from a methyl group axial to equatorial is minus 1.7. The A value for the methyl group then is just positive 1.7. That tells you it's 1.7 kcals per mole less stable to have the methyl group axial versus equatorial. All of this is relative to hydrogen because, of course, the two chairs of just pure cyclohexane are identical in energy. And so you can use this equilibrium constant and this free energy difference to get a sense for how big something is. Because remember, having something axial involves both torsional strain and 1,3 diaxial steric repulsion. So a few trends, you don't need to memorize A values and all. You get to look things up on my exams anyway, so memorizing numbers isn't that useful. The A value is a measure of steric size and not necessarily a measure of volume. In other words, embedded in the A value is lots of contextual information. For example, the A value for an ethyl group, in which you replace one of the hydrogens of methyl with another methyl group, is only 1.79. That's not very different at all from that of the methyl group. Why might that be? Well, let's draw an ethyl group in an axial position, and let's note that you can rotate around carbon-carbon bonds. And so the ethyl group can rotate to get its methyl group out of the way, and the molecule basically feels like it's just got a methyl group there. So even though in terms of volume ethyl is bigger, sterically not as big, not as bad as the methyl group. I mean, it's worse than the methyl group, but only by a teeny bit. Yeah, Brennan?
Kate asked, what do beta-lactams look like?
What do beta-lactams look like? Kate, if there's time, I will do that at the end, if that's okay. All right, anything else while we're paused? If, on the other hand, you start to take more of those hydrogens at that carbon attached to the ring and start to replace them with other methyl groups, it starts to get increasingly worse. So the group I've just drawn is the isopropyl group. I will abbreviate that with a lowercase I and a PR. You don't have to know that it's called isopropyl. I just will use that term in lecture, so it'll be good for you to follow along. That A value increases by a lot, and then it gets even worse by a larger amount when all of the groups attached to the substituent are methyl groups, because at that point none of them can get out of the way, and the A value there is 5.5. So this now allows us to make some qualitative judgments. What if we had a situation where we had a molecule like this and we wanted to consider both possible chairs? I'm going through the drawing kind of quickly, but hopefully as you review, you'll be able to see that these are the same molecule. Note that in both of them, both of the substituents are up, and only over here, methyl is equatorial, and over here, methyl is axial, and so on. So based on A values, go ahead.
So in the one on the left, it's equatorial, but does it still contribute to any strain or like worseness in the A value, even though it's not axial?
So the A value is is measured just for like one substituent on the ring, equatorial versus axial. So it isn't going to capture any additional problems you get from, say, having two things on adjacent carbons. Because I agree, you might be worried about interactions between the methyl group and the T-butyl group, which are both gauche to each other. But there's no other way to do it, actually, in this molecule because they're on the same side of the ring. So you're right. If you were to compare this to another molecule with the same number of carbons but with them arranged differently, you might say something about the relative stability. I think that's kind of tough to do. What I would expect you to do is look at these two chairs and decide which one is more stable. And so which do you think? One on the left is more stable. Yep. Qualitatively, you know, because the T-butyl group looks bigger than the methyl group. Also, when you compare A values, you can tell that it would be worse to have the methyl group. Worse to have the T-butyl group axial. All right. There are a few other sort of surprises with A values. Let me give you an example. No, we'll just be simple and put a methyl group here and a bromo here. I'm going to draw real quickly the two possible chairs. You'll need to go back and convince yourself that I've done this correctly. All right, so which of these two do you think is worse? Okay, you're saying the one on the right. Why do you think it's worse?
Because it's got the carbon with 3 hydrogens.
Okay. Right, so the answer here in class was that maybe the fact that bromine is just one atom, whereas carbon's bonded to 3 atoms, makes carbon a little bit bigger. In fact, if you look at A values for the methyl group versus bromine, methyl is 1.7-ish, and bromine is actually 0.38. Okay, which, remember, 0 is for hydrogen. So this would tell you sterically bromine is smaller than the methyl group. And that maybe should be a little troubling because we've made sort of a big deal about how atomic radius increases as you go down the periodic table. It gets weirder still when you consider the other halides. Fluorine is almost as small as hydrogen, basically a 1-to-1 equilibrium between axial and equatorial fluorine on cyclohexane. You go up to chlorine, which is bigger, and the A value does go up, not by a huge amount. You go to bromo, which is even bigger, and the A value drops. And then you go to the even larger iodide, and the A value goes back to what it was for chloride. And what you've got here are two offsetting effects. You've got the fact that radius increases as you go down the periodic table, and I made this mistake last time. I'm going to have to rearrange things so that that's true. Radius increases, but also bond length increases. And if you look back at our drawing about 1,3 diaxial interactions, those would get a lot less troublesome if we made this bond longer. And that compensates somewhat for the increased size of bromine. You've got larger size, but you're also further away, and so the effects sort of cancel out. And so bromine is not as big sterically as you would expect it to be just from consideration of volume. So context matters, structural details matter, and yes, this is the most stable conformation because you keep the group with the largest A value equatorial. And that's the general principle. Keep the most stuff equatorial. All right. Now, as I just stated it, there is a potential for misunderstanding that people make on exams, which I will now disclose to you so that you can avoid making it in the future. And therefore I can wash my hands of whatever mistakes you might make. A typical exam problem might go like this. I'm drawing a molecule. This is another carbohydrate. And then I might ask, which of the following options is the most stable chair conformation for this molecule? Now remember that there are only 2 chairs possible for a given molecule. So if there's more than 2 options, some of them have to be the wrong molecule. So let me show you a couple of options. We'll pretend this is multiple choice format. And we'll see how far we get. And because we're all here and I'm trying to make sure we finish in a reasonable amount of time, I'm not going to draw all the possible options that I might have otherwise done. Oh, dang. Sorry. I'm talking and trying to think at the same time, which is always dangerous. Whoops. Okay. So I might show this and a host of other options and say which of these is the most stable chair of the molecule to the right. Now, a mistake that many people often make is they just memorize the molecule with the most stuff equatorial is more stable. And they forget the principle that up stays up and down stays down. So some people are inclined to select A. A is the most stable chair of this molecule on the left. A is wrong. It is not even kind of right. See if you can figure out why. I'll give you a hint. This actually isn't, in addition to being a question about most stable chair, it's also a question about whether you got the relative relationships between the groups around the ring correct. Might help for the discussion if we number the atoms. Okay. Do you see the problem? Marianne from home says that one of the OH groups in A is down equatorial when it should be up. I believe you're talking about this OH group on carbon 4 is down, whereas in our drawing from overhead, that group should be up. Carbon 1, yeah, you got a similar issue. It's down here, but up here and should be down. Okay? So before you even worry about whether it's the most stable chair, you got to get the up-down relationships right. So B, does it have all the up-down relationships right? Carbon 1, a down OH group. Carbon 2, a down OH group. Carbon 3, up. Carbon 4 up, and carbon 5 up group. Yeah, we got all the up-down relationships correct. Now we would need to draw the other chair, which I attempted to do here in D. I'm not sure if I got it. I think pretty close, yeah. You would need to draw the other chair and then say which one is more stable. Now, between B and D, what's your choice? What do you think? B is more stable. Why? Because in B, more of the groups are equatorial and more of the larger groups are equatorial, right? The CH2OH group has got to be somewhat like a methyl group or an ethyl group. The A value for hydroxide, according to your study guide, is about 1. So it's worse to have a methyl type group axial versus a hydroxyl axial. B keeps 2 hydroxyls axial, 2 equatorial, and the methyl group equatorial. D is just the opposite of that. So yeah, B is the right answer. And I will tell you, probably 25 to 33% of you in the past, of your peers, have made this mistake of choosing A as the correct answer. Why? They were in a hurry and they just memorized equatorial good, axial bad. And so your understanding needs to be more nuanced than that. I think that takes us through the end of chapter 4 and a bit into chapter 5. So finish your study guide 4, it'll be due tomorrow, and on Friday we'll continue in with chapter 5.